Hello everyone. I'm Dr. Amala and Joice, Assistant Professor of Chemistry, Holy Cross College, Trichy. Today we are going to see about properties of nanomaterials. New technologies require new materials with superior physical, chemical and mechanical properties. The unique properties of materials due to ultra-fine particle sizes were recognized early in the 20th century. Ultra-fine particle sizes means which is nothing but nanomaterials. So nanomaterials refers to the class of materials with at least one of the dimensions in the nanometric range. The size of nano is 1 nanometer is equal to 10 power minus 9 meter. Properties of nanomaterials: physical property, electrical property, optical property and mechanical property. Physical properties: large surface to volume ratio proportional to the inverse of particle size r of nanomaterials changes the role played by the surface atoms in determining their thermodynamic properties. 4 pi r squared divided by 4 by 3 pi r cubed is proportional to 1 by r. Melting point: for a given bulk material, its melting point will be lower if it is in nano-sized. It is because the number of surface atoms increases when the size is decreased to nanoregime and the surface atoms are more easily removed than the bulk atoms. So, the total energy needed to overcome the intermolecular forces that hold the atom fixed is less and thus the melting point is lesser. Here you can see in this image, in the bulk catalyst, there are only 3 atoms are present. But you can see in the nano-size catalyst, there are more number of atoms present at the surface. Electrical property. There are 3 different categories of materials based on the electrical property. The one is conductor, the second one is insulator, and the third one is semiconductors. The energy separation between the valence band and the conduction band is called as the band gap, which is denoted as Eg. The energy band gap determines whether the material is conductor or insulator or semiconductor. The quantum confinement causes the energy of the band gap to increase in nanostructured materials. At very small dimensions, when the energy levels are quantified, the band overlap present in metals disappear and is actually transformed into a band gap. This explains why some metals become semiconductors as their size is decreased. Optical property. Nanomaterials exhibit very different optical properties such as color and transparency compared to bulk materials. One of the distinguishing property of metal nanoparticles is their optical property, which are different from their bulk counterpart. This is due to an effect called localized surface plasmon resonance (LSPR). When the light hits a metal surface, some of the light wave propagates along the metal surface, giving rise to a surface plasmon, a group of surface conduction electrons that propagate in a direction parallel to the metal vacuum interface. When a plasmon is generated in a bulk material, electrons can move freely in the material and no effect is registered. In case of nanomaterials, the surface plasmon is localized in space, so it oscillates back and forth in a synchronized way in a small space, and when the frequency of this oscillation is same as the frequency of the incident light and the plasmon is said to be in resonance with the incident light. This effect is called localized surface plasmon resonance. The LSPR energy is not only dependent on the size but also the shape and the distance between nanoparticles. So, by changing these parameters, LSPR energy can be changed and nanoparticles display colors which are not in their bulk form. Here you can see in the image, gold nanoparticles display colors like red, purple and orange depending on the size, shape and surrounding media. For example, 15 nanometer gold particle exhibit ruby red color, 50 nanometer exhibit green in color, 100 nanometer exhibits orange in color. Mechanical properties. The tensile, work hardening, creep, fatigue, and deformation behavior of nanocrystalline materials are significantly different from that of their bulk counterparts due to the complex interaction of the defect structures. Some peculiar mechanical properties of nanomaterials are Elastic moduli are found to be 30 to 50% lower than in conventional grain size material. Hardness and strength are very high with values up to 7 times higher than those of conventional materials. Tensile and compressive strength also high in nanomaterials. Ductility is observed at low temperature in brittle ceramics with nanoscale grain size. Carbon nanotubes are 100 times stronger than nanosteel. The frequently asked questions are, these are the references. Thank you.